All right, class, hopefully this started, but today we're looking at biomes. Um, Primarily what we're looking at today is what causes the biomes to be where they are. So if we get started, we have a little review. You can categorize all the biomes on Earth in several different bigger categories. So we say that there's aquatic biomes, so that's just water-based biomes that include fresh and marine water, so marine water would be salt water. There's deserts. Deserts can be both hot and cold, so they're really dependent on rain. And for deserts, we're primarily looking for very, very, very little rainfall. And then there's different types of forests. So we had the tropical rainforest, so you might picture that being in Brazil. We have the temperate forest, so you might picture that as being in New York State in the United States or in Germany. And the boreal, or the coniferous forest, which is also called the taiga, so lots of names. And that I normally would think of that as being in the regions of Canada. Then we have grasslands, and grasslands can be temperate grasslands primarily, or also savanna, and they can also include some tropical area grasslands. And then we have tundra. So tundra can be considered those Arctic zones, but they could also be alpine. So alpine means like on the top of a mountain. Okay, so just like we talked about in class in the first block, that if you go even to a really warm place with big enough mountains, that if you climb the mountains in the middle of summer, it could still be really cold up there. So it could be like a tundra-like environment on the top of a mountain, even if you're located, really close to the equator. Okay. So looking at the biomes again, so forests, I think I might make a note catcher for you guys with some pictures, and you know how good I am at drawing, so that will be just especially for you guys. But I want you to be able to kind of picture the biomes when you hear the names. So when you think about forests, we've got tropical, temperate, and boreal. They vary depending on temperatures, but also rainfall, because plants have different demands for rain. So if we think tropical, that's what we think when we think of South America. You might think of Asian countries. They're hot, they're humid. There's many living things there. They're really a hot spot for biodiversity. And then we have those temperate forests. So we said this has a lot of deciduous trees, so trees that lose their leaves in the fall and then grow them back in the spring. And that I always think of like upstate New York. If you go to upstate New York, has beautiful fall colors, and then all the leaves drop, and then in the winter there's really just a lot of just barren trees, but then there's a beautiful bloom again in the spring. And then the boreal, or the taiga, that's primarily coniferous forest. And remember we said coniferous. So coniferous refers to cone-bearing trees. So we normally think of them as trees that have needles, like pine trees, though not all coniferous trees have, exactly needles like a pine tree has. So we characterize them primarily by the fact that they have those cones. So you can think of that as Toronto or Moscow, so more northern regions. Here's some just beautiful pictures. So I want you to be able to associate these pictures with a specific zone. So I think we'll work on that for making like a note catcher so that you have all that information that you need. So why the heck are these biomes where they're currently located? So we said that the main issues that we look at are climate. So that's precipitation and temperature over a long period of time. So weather is like what's happening right now, what's happening in the moment. But if you take weather over an extended period of time and you average it out, that's climate. Now there are other factors that come into play, and we'll see that a little bit later this week. So that's terrain. So is it mountainous? Is it highly sloped? What does the surface of the earth look like there? Though that is taken into account. And the altitude. So how far up the mountain might you be? So how tall is the mountain? There are mountains that are quite small, and then there's mountains like Mount Kilimanjaro, okay, or the Himalayas that are extremely tall mountains. So you're going to see some different stratification of environments on those really tall mountains. So pause. This is pause and go to the flashlight demo. So I want you to do that because it's just supposed to build background information for what we're talking about next. So pause this, watch the demo, and then come back to the notes. All right? Okay, so back to why are the biomes where they are. So we saw the flashlight demo and we talked about the concentration of light energy over a surface area. So of course when we're talking about Earth, we're talking about the solar energy that hits Earth from the sun. And we're thinking about how concentrated or how spread out that energy is at the surface of the Earth. So we know the surface of the Earth is a sphere, and if we're just thinking about the positioning of that sphere, versus the solar energy moving toward us, the solar energy is most concentrated at the equator or near the equator. Okay, so that would be that 90-degree angle. And then as we move, toward the northern or southern poles, so as we move from the equator toward the poles, so at higher latitudes, we see that the energy becomes more dispersed, so more spread out. So that means there's less solar energy per unit area. And that does a lot for the amount of heating of the Earth. This is a good term, so just thinking some earth science here. So this is called the angle of insolation. So that's the angle at which the sunlight or the solar radiation is contacting the Earth. So we can see right around the equator, that's 90 degrees, and then the angle becomes lower and lower toward the poles, and we see these bigger shapes traced on the surface of the Earth. So just showing that the amount of solar radiation is more dispersed or more spread out. So we would expect this surface area with more energy per unit area to increase in heat, so to heat up faster than you would expect this to heat up, okay, because there's just less energy per unit area. So this also relates to seasonal changes. So if we look at the Earth, and I hope you have some background knowledge in this from maybe middle school, I'm not sure when you guys last took some earth science, I think maybe middle school, but the Earth is tilted on its axis. So if you see this, it's not the best quality picture, but the Earth is tilted at 23.4 degrees, okay, as it revolves around the sun. So as the Earth changes position, that axis always points off to the same side. So it's actually pointing toward the same location in space, if you will. So there's not a lot of wobble there. So if we look, as the Earth moves from spring to summer to fall to winter, the angle at which the sunlight reaches the Earth changes at different locations. So in general, the sunlight always is going to be fairly concentrated in the tropics region, so near the equators between the Tropic of Cancer and the Tropic of Capricorn, okay? But it's going to vary a lot at those northern and southern regions. So if we look at the extreme, so if I look over here at the extreme on this side, I see that in this position, the northern hemisphere is actually pointed toward the sun. So at this position, the sunlight reaching the northern hemisphere is going to be at a higher angle, which means the sunlight is going to be more concentrated, and that hemisphere is going to heat up more. So that means it's summer in the northern hemisphere. Now, opposite of that, in the opposite position, we see that the southern hemisphere is actually pointing toward the sun, meaning that the sunlight reaching the southern hemisphere is going to be more concentrated, meaning that the southern hemisphere will thus heat up more, and it's going to be summer in the southern hemisphere. So I always think this is interesting. Like, I met people over a winter break who were in Venice. I was in Venice with my husband, and they were in Venice from Australia. So they were coming from a very summery location where it's very warm into this cooler, more wintry environment. And I just find that really interesting. So that's their vacation time. They came to the northern hemisphere and the climate was totally different. Okay. Pause. So for our next portion, I'm going to ask that you watch the convection demo. Okay, watch it, think about it, and then come back so that the next stuff makes sense. All right? So back to this. Why are the biomes where they are? So one of the things we can look at is the patterns in the ocean currents, so that's just how the ocean moves, and how the winds move. You should be considering things like, if we're looking at the winds and we're looking at the ocean, knowing that the equator region heats up more than the poles, we're always thinking about how that heat then is going to be transferred from the equator toward other regions. This also says to consider the fact that winds blow from high to low pressure areas, and we'll look at that in a minute. So this is some good weather information. And then water is responsible for transferring a lot of heat, so that is just true. So ocean currents can impact weather in many areas, as well as the amount of available the amount of available water can impact the climate of a region significantly. So here we see this tricellular model. So in the demo, you saw this convection current. So you saw it. In that gigantic beaker, there was a convection current. We saw that material heated up. Okay, so it heated up, it rose to the top, then it cooled, and it fell. And that pattern will continue and continue and continue, and it created this circular motion. So we see this here. So I want you just to focus on what it's showing that this is the equator, and then it would be the same on either side. So moving from the equator toward the poles. Okay, so this is toward the North Pole. It would look similar moving toward the South Pole if we showed the other side, right? So things to consider. First off, here is the equator. We have a lot of heat, so heat is causing materials to rise, okay? So the air is rising. We also see here that this is representing the fact that maybe water is evaporating. So water is evaporating, it's rising and it's cooling, okay? Which is going to cause some more precipitation in this area where the rain will fall again. Then we see here, okay, also, another thing to think of, when the air is rising up, so when you see patterns like this, so this is air moving away from the ground, so that's low pressure. Okay, this would be a low pressure area. On the other hand, if we go toward the other side of this cell, so this is the Hadley cell, we see the cool air falling, and I always think of it as kind of pushing on the surface of the earth. And in that case, when it's pushing on the surface of the earth, this is high pressure. Okay, so it's moving toward the surface of the earth, that air is. Things like thunderstorms and rain are typically associated with low pressure, and then high pressure, like if there's a high pressure front, you would normally think of that as a sunnier, clearer day. So here we have more high pressure, just in general, not always, but these are the climate patterns. Here we have lower pressure, more rain. And you see these patterns continue in these other cells. Okay, so you see them continue. So as this one's pushing down, okay, it's pulling some air over. This air heats up, rises, cools, and falls, all right? So you see they kind of function next to each other, almost like gears, right? So if one is spinning this way, so I'm going to describe this as counterclockwise, then the one opposite it is spinning clockwise, right? And then our northernmost one is again spinning counterclockwise. So as these things rise together, so the air rises together, some will go off to one side, some will go off to the other side, okay? And we create those circles. So this is a pattern that you would expect to see, right? Now, there's this called a tricellular model. So there's 1, 2, 3 cells within each hemisphere. So it would be the same for the southern hemisphere, okay? So we'd get this cell moving this way clockwise. Then we'd have another cell next to it moving counterclockwise. And then the South Pole, the South Pole cell, okay, would be again moving clockwise. Right? So we always see two next to each other kind of moving up together, two next to each other where they meet moving down together. Okay, here up together. So similar to Gears. I'm not sure if you've ever played with Gears, but we could maybe watch a little video